Okay, so here we have question 7. Okay, and we're given a graph below, and the graph has the function h at x, where h at x is equal to 2x times e to the power of x plus 3, and x is all real numbers. Yeah, great. So for part A of the question, we're asked to find the value of y where h intersects with the y-axis. You can also call this the y-intercept, okay? And we know for the y-intercept, or h rather, the function will intercept with the y-axis when x is equal to 0. So with this fact, we can substitute x equal to 0 into our equation h at x. So h at 0 multiplied by 2 times 0 times e to the power of 0 plus 3. And we know that this term being multiplied by 0 will become 0, so h at 0 is equal to 3. So the answer for question A is 3. Okay, so we're now doing our next part of the question where we're asked to take the derivative of h of x, and we will do that by using the product rule, where for y is equal to ux, we take the derivative of our first term, or in this case our second term, and we multiply it by u. Then we take the derivative of our next term, u, and multiply it by v. So if we have h at x, so for h at x, we will have the derivative of our first term, x, which just becomes 1, and we will multiply it by our second term, e at x, and then we will take the derivative of our second term, e at x, which is just going to be e at x again, so that we get 2x times e at x and 2 times 1 times e at x, and that will be the derivative and answer to our question B. Okay, great. Now for question C, we're asked to find the coordinates of A, and if we look at the graph, we can see that A is a local minimum. But even more so, what this means is that the derivative at this point should be equal to 0, since there's no upward or downward change. So to find the coordinates of A, we can set our function, our derivative here, equal to 0, and then solve for the x value. So 2 times e at x plus 2x e at x. We can factor out the 2 times e at x to get 1 plus 2x. And then solve for each of these factors to find our x value. So if we equate the first term, 2 times e to the power of x, to 0, we will see this has no real solutions. Real solutions. But if we do this with our second term, 1 plus 2x equal to 0, I seem to have made a mistake because there is not a 2 here, as a matter of fact. So it's actually 1 plus x, and that will mean that x is equal to -1. So now using our x value, we can then substitute this into our initial function h to find our point at A. So for h at -1, we'll get h is equal to 2 times -1 times e to the power of -1 plus 3. And then if we solve for that, we find that our equation becomes 2 over e plus 3. So then our coordinate for point A, is -1 and then -2 for E plus 3. It's not pretty, but yes, that is our coordinate. And that is our answer for part C. For our next question, DI, we're asked to show that the second derivative of our function h is equal to 2x plus 4 times e to the power of x. So to find our second derivative, we're just going to use the first derivative that we've already taken and take the derivative again. So we'll get h double prime of x is equal to 2 times the derivative of e to the power of x, which is just e to the power of x. And then for our second term, we will again be using the product rule. So we'll first take the derivative of 2x, which is just 2, and that will be times e to the power of x, plus the derivative again of e to the power of x multiplied by 2x, which will just become 2ex, e to the power of x. And then we can collect like terms so that our equation becomes 4 times e to the power of x plus 2x times e to the power of x. We can then factor out this e to the power of x, and it will be multiplied by our term here, which is 4 plus 2x. And if we look back at our question, again, we can see that these two terms. All right, so for our next part of question D, we're asked to find the values of x that make our graph h concave up. And we could look at the graph and figure this out probably, but we can also use the second derivative test. And if we recall from the test, h at x actually, will be concave up when h double prime, so the second derivative at x, is positive or greater than 0. So if we look at our second derivative here, e to the power of x multiplied by 4 plus 2x, we can solve for these values for when the function is greater than 0. So if we look at our first term, set that greater than 0, well, we know that e to the power of x will always be greater than 0. So it will be based on our second term, which is 4 plus 2x. And we will set that greater than 0. And then if we move further and rearrange our terms, we can say that 2x must be greater than -4, and therefore x must be greater than -4 over 2, which is also just -2. So x must be greater than -2 for a function to be concave.